So the timing or sequence of presenters was obviously well planned. So as Zach mentioned, we work together under the same umbrella, CATT, the Center for Advanced Transportation Technology. I work specifically for CATT Lab, which deals more with the visualizations and building online analytical tools for practitioners. So building off some of the exploratory research that Zach and his team worked on, CATT Lab is now in the process of developing online tools so that end users, practitioners from both private and public agencies can go in and utilize this data to help address some of their issues they have with, in this particular case, we're going to be talking about handling traffic congestion, but as we mentioned, there's other potentials for using this for looking at sustainability and safety as well. So in my presentation today, I'm going to go over a brief background and motivation for developing this tool, again, building on what Zach said. Reiterating a little bit about the data itself and how it's processed so that we can ultimately get to a point where it can be visualized and used to answer transportation engineering type questions. Then to sort of illustrate how we envision this tool, which again is not deployed yet, it's in development. We have some sample applications of how we think that this tool can be used, and I'll kind of walk through the initial mock-ups of some of the visualizations and how we can use them to, or use the interpretations from those visualizations to answer certain questions. And then I'll talk briefly about our conclusions and the future work. So a brief background on the project itself and the tool that we're trying to develop. So as you guys are probably familiar, OD data is the cornerstone of demand and travel pattern analysis. So traditionally it's been done using surveys. So they would send out questionnaires to people in a certain area, asking about their travel patterns and also collecting socio-demographic information about how many people lived in their household, what was their household income, things about their race, how many vehicles they owned, and so forth. So it's a very time-consuming and costly process to do that, and it's usually only updated every couple of years depending on the area and the funding resources available. But as Zach mentioned in his presentation, that GPS data is becoming more and more prevalent, and getting access to it is allowing us to develop real-time, or not real-time, but real-world observed OD patterns from vehicles equipped with GPS data. So we're working, again, with the state of Maryland on a data set that was for the year of 2015 to look at how we can use that data to address some critical considerations. And as I mentioned, in this particular presentation, we're focusing on congestion. So our objective and motivation is to dig into this data to see how practitioners can use it to address these type of problems, starting with understanding congestion. So the full data set, just to give you an idea of how large the data set is, and this is just 4 months within the state of Maryland. So any point that had this technology and had at least one waypoint within the boundary of the state of Maryland was included in the data set, which we got from NRICS. So the full data set had almost 20 million trips for that 4-month period, and over 1 billion waypoints associated with those trips. For the visualizations that I'm showing today, we focused just on the trips that occurred in July of 2015, which was almost 5 million trips and over 1 million or 100 million waypoints. So before we can get into analyzing the data, as I think Zach mentioned, there's a lot of pre-processing that has to go into this. The data comes in as raw lat and longitudes, which may or may not fall on an actual road segment, so we have to do some data cleaning. In addition to snapping the individual points to the road network, we have to also come up with a way of understanding what the route is. So the ping intervals, when we get updates from a particular trip, it could be at 1 second, but in some cases it could be over a minute. So we have to make some assumptions about what the traveler did between those 2 points. On an interstate, it's pretty easy to understand. If you're in the middle of a central business district where there's several blocks and one-way streets and you wait 1 minute, there's 3 or 4 different ways you can get to that point. So we come up with a way of handling that and coming up with what we think is the most likely path that the traveler used to get to that point, using Markov chain analysis, which I won't go into any detail today. So a sample application that we think could be used for this data is to find a road segment that is regularly congested for those that live in the DC area. I-270, southbound during the AM peak, people trying to get onto the Beltway to access Bethesda, Northern Virginia, and Washington, D.C. It becomes regularly congested between the hours of 6 and 9 a.m. So we decided to look at this southbound segment of I-270 to see how we can better understand how this congestion forms using trajectory data. So the first idea was to look at an OD map. So building off of the OD matrix, we can actually look at clusters of where these trips come from, and as I'll show in the next slide, where they're going to, what was their average departure time, and is there any variation in that departure time. So here we're showing at the county level, and you can also go down to the traffic analysis zone level. We're even working on a tool where you can customly select a trapezoid and get the trips that fall within that particular region. But in any case, the application is still the same. We can see that for July, in Montgomery County, Maryland, is shown here, the county where this I-270 segment is located, had over 6,000 trips. The average departure time was 6:40 a.m. With a standard deviation of 53 minutes that used this segment. So it gives us an idea of, okay, we know that this is a congested segment, but where are these trips coming from? So this might be used to drive decisions on incentivizing carpooling, building HOV lanes, other traffic management strategies such as telework, flex hours, which sort of relates to the next plot where we look at that same segment, but now we're just looking at the destinations, again, clustered by county. As you might expect, Montgomery County was one of the top ones, the county where that segment is in, but we also see Washington, D.C. and Northern Virginia. So this is Montgomery County. You can't see the road because it's covered by the data label. Washington, D.C. and Northern Virginia are huge employment magnets for the area, so it's not surprising to see that those are the ones that have the most destinations for this time period. And similarly, we see that within Washington, D.C., within this data set that we have, over 1,700 trips were destined to Washington, D.C. that used that segment. Their average arrival time within D.C. was 7:18 a.m. with a standard deviation of 1 hour and 2 minutes. So furthermore, in addition to the maps, we can look at the more traditional way of looking at origin destination patterns using a matrix. Here it's just a heat map showing red with ones with higher patterns between those two OD pairs, going down to yellow with fewer and gray being none. So again, remember that this data set is limited in that it's only covering approximately 1 to 5% of the total trips. So just because we see zeros in some of these cells doesn't mean that the true origin destination is zero, but we can use this to understand a more general pattern of the trips using this data set. We can also, because we have the trajectory data, we can look at the routes that are used. So again, these are all trips that crossed the analysis segment shown here in yellow on I-270 southbound. We can show the full trace of the trips, of every single trip that used it, with thicker lines being trips that had more volume on it within this data set. So not surprisingly, many trips come from the northwest of that segment to gain access to 495, again, to get to the employment magnets of Northern Virginia and Washington, D.C. and Bethesda, Maryland. So we can see that 270 and 495 are the ones that are a little bit thicker than the rest, and we're working on additional filters so that people can go in and visualize the top 5%, 10% of the routes that are being used, so this map isn't as cluttered. Also knowing what the O's and D's are for particular trips, not just counting the number of trips, but we can also have a better understanding of what the full travel time is between those two origins and destinations. So it's important to note that this is slightly different than what traditional probe vehicle data can provide. They look at travel times on particular segments, but they don't tell you anything about the full trip. So you have to make some assumptions about adding up the travel times on individual segments from the traditional probe data to get that. But this sort of relaxes that assumption. Now we have the full travel times of individual trips getting from a particular origin and destination, which we can show as histograms like this would show the raw number of trips that fall within a given time bin, and we can also normalize that to look at that as a percentage of those trips between that OD pair, as shown as in these two figures. So to summarize what I've discussed today and discuss the future work paths is that trajectory data provides some very valuable trip level information that had previously been hard to collect. And it's still in its very infancy, but we're working at the University of Maryland CATT and CATT Lab to develop some applications so that we can utilize this to address real-world problems. So we're working on investigating the pairing of this trajectory data with traditional surveys, because one thing that trajectory data is limited in is it has nothing about the individual drivers, how many people are within the vehicle for individual privacy purposes, obviously, but if we compare that origin and destination information with data that we collect from traditional surveys, such as household income, number of vehicles owned per household within that region, we can come up with better understanding of the types of people that are being affected by congestion, for instance. And then as Zach mentioned, we're working at CATT Lab on ways to scale up these trajectory observations. Right now, we're only getting 1 to 5% of the traffic flow, but we want to be able to get a better understanding of what the full potential of using this trajectory data to understand what the volumes were, and hopefully use that also in understanding travel demand patterns for things like OD matrices and route usage and travel times. So that concludes my work. This is my contact information, and I'll be happy to take any questions.